Welcome to week 8 of Calculus 3. We're going to continue discussing differentiability from last class. In this first video, though, we're going to do a little bit of review from the last class and also review a little bit of what we talked about in Calc 2, believe it or not. Okay. To start off, I would actually like you to do a little bit of thinking on your own. So, in Calculus 1, we discussed the linearization at a point. Okay, and we saw that there was this L of x function, and it's equal to f of a plus f prime of a times x minus a. And I'm kind of curious why that's the formula for linear approximation. So I want you to think deeply about this. Pause the video, spend 3 to 4 minutes, and just think this over. Alright, and so hopefully you had some fruitful thoughts, and really the crux of this idea is that, well, really this is the tangent line. Line at the point. Right? So what we could do is, well, we can remember first of all that, okay, there's many different equations of a line, or forms of the equation of a line, right? So there's y minus y naught is equal to m, x minus x naught, and that's point slope form. There's also the standard y is equal to mx plus b that people butcher, and then there's also the standard form, which is ax plus by is equal to c, right? Okay, so well, I want to actually look at this one, okay? If I know that I have a tangent line, right? Okay, well, the point that I'm going to use is going to be a comma f of a, okay? And for a tangent line at that point, right, I know that the slope is really f prime of a. Okay, so then if I use that point slope form, right, what do I get? I believe I get y minus f of a, right? And then that is equal to f prime of a times x minus a, okay? And if I just solve for y here, I get y is equal to f of a plus f prime of a. Oops, let's erase that. Okay, and we can call that L of x. Okay, so tangent line at a point is the linear approximation, right? And so that's where this all comes from, at least in Calc 1, and then in Calc 3 now, we're starting to go up in dimensions. So as we saw last class, we talk about tangent planes, right? And so just a reminder from last time, we said, okay, well, we reviewed Calc 1, that's our standard definition of a derivative, right, and something being differentiable. And we could actually write this logically as being equivalent to that linearization, right? So that's at L of x, okay? So that's the tangent line, right? And so then as we go up in dimensions, we get vectors, right? And so we looked at that R2 case to R, and when we did that, we got this h of x, which acts a lot like that tangent line, but now this is our tangent plane, okay? All right, and then last time we introduced the notion of partial derivatives and defined h of x as this following, so it's that point, and then we had that kind of slope in the x direction, the slope in the y direction, and then we included each component. Okay, so that's where we're going to pick up today. Okay, so just as a quick follow-up here, why do we want to use that? Well, answer number one is it is nice. Plain and simple, right? It's linear. So it's linear, right, in each of the factors, right? So there's no squares or exponentials, trigs, etc. Okay. The second thing is that if I look at these vectors, right, so 1, 0, and then the derivative of f with respect to x, and similarly with the y. Oh, and I forgot a parentheses here. Okay, those actually happen to be tangent to the graph at our point. Okay, and just note that these vectors correspond to the function, or to the tangent plane. Okay, coincidentally, if we look at their cross product, okay, we know that each of these vectors are on the tangent plane, since they are both tangent to f. Okay, so if I look at their cross product, I think I get something that would be normal, right? Normal to the tangent plane. Okay, so let's look at their cross product. I, j, and k. And let's see, so I get 1, 0, f sub x, 0, 1, f sub y. Okay, and then we get to do the cross product, which I will leave it to you to show, but I believe you get minus f sub x, and then this would be at the point AB. And then similarly you would get negative f sub y at AB. And then in the third component you just get 1. Okay? And so this is actually the normal vector at A, B, f of A, B. Okay, again, assuming that these vectors are the tangent vectors. Okay, so then why is this good for us? Well, back in Calc 2, we talked about the equation of a plane, right? And we said the equation of a plane, we can take the normal vector and dot it with a vector minus a vector that is on the plane, or a point, really, okay, and that is equal to 0. Okay, right, so then I think, right, I can say, well, I'm going to use the normal vector from above, so I can write this as negative f sub x, and I'm going to omit the AB for the time being, minus f sub y, and 1. Dot this with vector x, which, okay, we can write this out since we're in 3 components. X, oops, and I want to put this in square brackets, or angle brackets, x, y, and z, minus a, b, f of AB, okay, is equal to 0. And what I get is, let's see, okay, so I get negative f sub x at AB, and here I'm going to include the notation, and then times x minus a, and then minus f sub y of AB times y minus b, and then plus z plus f of AB. Oops, and that should be minus, I'm sorry. Z minus f of AB is equal to 0, okay? And coincidentally, if you happen to solve for z, I think you get h. So if you solve for z, you get z is equal to that equation that we had for h of x, for our tangent plane, or for the plane that we saw before, okay? Or for the linearization at that point. Okay, so that's why it's kind of nice, and another reason why we have that h of x. Okay, so that's a little bit of review from last week and justification for h of x. In the ensuing videos, we'll introduce a little bit of notation and actually finish up derivatives.